Welcome back to G Fun Facts Online. It is December 27th, 2025. If you have been following the tech industry for the last decade, you know the narrative has been dominated by one piece of hardware, the graphics processing unit, or GPU. We have spent the last 10 years building what are essentially cathedrals of computation, massive data centers that consume the power of small nations, all to train models that have grown from billions to trillions of parameters. But as we close out this year, the industry has hit a wall. It is a wall that Moore's law can no longer scale over, and it marks the end of the digital monopoly on artificial intelligence. Today we are doing a deep dive into the analog renaissance and how physics is finally solving the AI energy crisis. To understand why this shift is happening right now, in late 2025, we have to look at the fundamental flaw in the way we have been building computers for the last 80 years. It is called the von Neumann bottleneck. In every digital GPU, CPU, or TPU you have ever owned, there is a strict separation of church and state. Data lives in memory, which is DRAM, and processing happens in logic cores. This means that for every single calculation a computer performs, data must be fetched from memory, moved across a bus, computed in the core, and then written back to memory. In the era of large language models like GPT-5 and Claude 4, this architecture is a disaster. These models require a constant shuffling of weights. The data tells us that this movement alone consumes up to 90% of the total energy in a data center. We are effectively burning gigawatts of electricity just to move numbers from one side of a chip to another, not even to calculate them. This inefficiency has birthed a crisis. Data centers are now rejecting new cluster requests because local power grids physically cannot supply enough juice. Furthermore, the dream of edge AI, running powerful models on your phone or a drone without an internet connection, has remained a pipe dream because digital batteries simply cannot sustain the energy requirements of digital math. This is where analog matrix computing, or AMC, enters the frame. Now, when I say analog, do not picture the vacuum tubes of the 1950s. This is a sophisticated, nanoscale reinvention of computing. The core philosophy here is to stop trying to simulate mathematics with logic gates and start using the laws of physics to actually be the mathematics. By turning memory into the processor itself, analog chips are shattering the efficiency barriers of the digital age. We are seeing 100 times improvements in performance per watt. This technology promises to put the power of a massive data center into a device as small as a hearing aid. Let's get into the physics of how this actually works, because it is elegant in its simplicity. To understand why analog is winning, we must look at the fundamental operation of deep learning, which is matrix vector multiplication. A neural network is essentially a massive collection of weights, or synaptic strengths. When you ask an AI a question, your input is multiplied by these weight matrices. In a digital computer, this is a brute force process. To multiply a 1000 value input by a 1000 by 1000 matrix, a digital core must perform 1 million separate multiplication operations and 1 million additions, sequentially or in parallel chunks, moving bits back and forth for every single step. Analog computing cheats. It utilizes two fundamental laws of electricity. First, Ohm's law. You likely remember this from high school physics. Voltage equals current times resistance. If you pass a voltage, representing your input data, through a resistor, representing the weight, the resulting current is the product. The multiplication happens instantly, physically, and naturally. The second principle is Kirchhoff's current law. If you wire multiple resistors together, the currents naturally sum up. In an analog matrix processor, the neural network's weights are encoded directly into the conductance of memory cells. You apply the inputs as voltages along the rows of a memory array. The physics of the circuit instantly multiplies the voltages by the conductances and sums the currents along the columns. The result is that you can perform millions of multiply accumulate operations, or MACs, in a single clock cycle with absolutely zero data movement. The memory is the computer. This is often called in-memory computing, and it is the closest we have ever come to mimicking the human brain's energy-efficient architecture. Of course, the concept is one thing, but execution is another. In 2025, we have seen three distinct technologies emerge as the frontrunners in the race to kill the digital GPU. They are ReRAM, PCM, and Photonics. Let's start with resistive RAM, or ReRAM, which has become the gold standard for edge inference. ReRAM cells work by forming and breaking conductive filaments inside a solid dielectric material. By controlling the size of this filament, engineers can tune the resistance of the cell to represent a specific neural network weight. The big breakthrough happened just months ago when researchers at Peking University demonstrated a commercial process ReRAM chip that solved high-precision matrix equations 1,000 times faster than flagship GPUs, with accuracy actually rivaling digital fixed-point systems. This addressed the historic Achilles heel of analog, which was precision. In the commercial sector, companies like Mythic have been pioneers here. After navigating some financial turbulence back in 2023, their late 2025 M2000 series chips are now seeing deployment in drones and security cameras, delivering 30 trillion operations per second for just a few watts. Another player, Ambient Scientific, is pushing boundaries with their DIGAN architecture, blending analog Macs with 3D memory stacks for battery-powered smart devices. The second major technology is phase change memory, or PCM. This is the technology IBM is betting on. While ReRAM relies on filaments, PCM relies on heat. A PCM cell contains a chalcogenide glass, similar to the material in rewritable optical discs. By heating it, the material switches between a conductive crystalline state and a resistive amorphous state. IBM Research has spent years perfecting this. Their latest analog AI cores utilize PCM to store weights. The advantage of PCM is its stability and density. IBM's recent North Pole digital analog hybrid concepts have shown that you can run transformer models, the architecture behind LLMs, with 14 times better energy efficiency than 4-nanometer digital nodes. The nuance here is that PCM is temperature sensitive. The drift of resistance over time was a major hurdle, but this year has seen the introduction of active drift compensation algorithms that recalibrate the analog values transparently, making these chips viable for enterprise servers. The third, and perhaps most exotic technology, is photonics. If ReRAM and PCM are the evolution of electronics, photonics is a different species entirely. Companies like Lightmatter and Lumai are not using electrons. They are using photons. In an optical processor, data is encoded into the intensity of light beams. These beams pass through Mach-Zehnder interferometers, which are tiny prisms and splitters that interfere with the light. The interference pattern essentially is the calculation. The edge here is obvious. Light generates zero heat when traveling. The only energy cost is the laser and the conversion of data from electronic to optical. This year's parallel optical matrix multiplication, or POMMM, breakthrough proved that light can handle the massive tensor processing of AI in a single shot of propagation, drastically reducing latency. For real-time trading and autonomous driving, where microseconds matter, photonics is becoming the premium choice. Now, you might be wondering, why are data centers so desperate for this switch? It comes down to a startling metric that came to light in early 2025. GPU utilization in inference workloads often sits below 50%. Digital GPUs are designed for massive batch processing, crunching huge blocks of data at once. But real-world AI is bursty. A user asks a chatbot a question. A car sees a pedestrian. These are single, immediate events. Digital GPUs struggle to keep their thousands of cores fed with data for these small batches, leading to idle silicon burning power. Analog chips do not have this overhead. Because the weights are stationary in the memory arrays, they have zero setup time. You can wake up an analog chip, run a single vector inference in microseconds, and shut it down. This instant-on capability makes them the only viable solution for the massive scale-up of AI agents anticipated in 2026, where billions of autonomous software agents will require constant, low-latency inference. If analog is so superior, why didn't we switch years ago? The answer lies in the messy reality of physics. Digital is perfect. 1 plus 1 is always 2. Analog is probabilistic. 1.0 plus 1.0 might be 1.999 or 2.001. Depending on temperature, wire resistance, or electronic noise. For years, this noise made analog chips useless for deep learning, which requires high precision, especially for training. However, the algorithm hardware county design revolution of 2024 and 2025 changed the game. Startups like RAIN Neuromorphics realized that we should not try to eliminate noise, but rather train the AI to survive it. By injecting noise into the model during the digital training phase, known as quantization-aware training, the neural network learns to be robust. When deployed on the noisy analog hardware, the AI performs flawlessly because it has already seen that level of variance. Furthermore, the most successful architectures of 2025 are hybrids. They use analog arrays for the heavy lifting, the matrix multiplication, which is 99% of the work, but use high-precision digital circuits for the accumulation and activation functions. This sandwich approach gives the best of both worlds, analog efficiency with digital stability, and we cannot forget the 24-bit breakthrough. The recent work from Peking University using ReRAM achieved 24-bit fixed-point precision. This is a massive leap. Previously, analog struggled to get beyond 4-bit or 8-bit precision. 24-bit is sufficient for almost all inference tasks and even some training workloads, effectively removing the precision argument from the table. Looking at the industry landscape in December 2025, we see distinct tiers. The hyperscalers like Google and Microsoft are quietly integrating optical interconnects and analog offload engines into their custom silicon, such as TPUs and Mayas. They are terrified of the energy bill for the next generation of models and view analog as the only path to net zero AI. Then you have the establishments. IBM is positioning itself as the leader in enterprise analog, focusing on high-reliability server markets with PCM. Intel, through its neuromorphic Loihi line, is blurring the lines between spiking neural networks and analog compute, targeting robotics. And then there are the disruptors. We mentioned Mythic, the poster child for analog edge, putting desktop-class AI power into a $50 chip. There is RAIN AI, backed by heavyweights like Sam Altman, targeting the holy grail of analog training. Their equilibrium propagation algorithm attempts to replace backpropagation with a physics-based local learning rule. If they succeed, they won't just speed up running AI, they will democratize creating AI. And Lightmatter is leading the charge in photonics to solve the interconnect bottleneck, using light to wire chips together into massive supercomputers that act like a single chip. The implications of this technology extend far beyond just chatbots. We are looking at the foundation of 6G networks between 2028 and 2030. The next generation of cellular networks will require massive MIMO antennas processing RF signals at speeds digital DSPs cannot handle efficiently. Analog ReRAM chips are being designed to process these radio signals directly in the analog domain, skipping the power-hungry analog to digital converter entirely. And perhaps most importantly, for the average consumer, this is driving a privacy revolution. Currently, your smart speaker sends your voice to the cloud because it lacks the battery power to process an LLM locally. Analog chips solve this. In 2026, we expect to see offline AI assistants on smartphones that are as capable as GPT-4, but run entirely on device, preserving total privacy and working without a signal. To conclude, for 70 years, we have lived in the digital abstraction, pretending the world is made of ones and zeros. It served us well, giving us the internet and the smartphone. But AI is different. AI is nature-like. It is fuzzy, probabilistic, and massively parallel. It does not belong in the rigid, serial, binary world of the von Neumann architecture. As we look ahead to 2026, the transition beyond GPUs is no longer a research topic. It is a supply chain reality. The silicon wafers leaving fabs today are beginning to look less like logic gates and more like resistive tapestries. We are returning to the roots of physics to build the brain of the future. The digital age is over. The analog AI age has just begun.